let us try to use about 20 minutes to explain the last 3 questions of quiz number 1. Yeah. In quiz number 1, the last 3 questions, the miss rates are the highest. Yeah. For question number 8, the miss rate is 82%. Okay, yeah. Question 9, the miss rate is 23%. Question number 10, the miss rate is 91%. Yeah, okay, yeah. So here you can see question number 8 and number 10, the miss rates very high, above 80. Yeah, 80, 90, in that level. Yeah. All right, yeah. So let me explain these 3 questions. Yeah. All right. Question number 8. Yeah. F function is twice differentiable. Yeah. Twice differentiable here means the second derivative exists. Yeah. Yeah. So F partial derivative on x twice. Okay, all right. And the mixed xy, yx, y exists. Okay, yeah. Exists. Yeah. That's the, twice differentiable on a disk D, yeah, which implies, yeah, yeah. Can we say that these two, yeah, the same? Answer is no, yeah, because the condition is not strong enough. Not strong enough, because you only have the exists part. You miss the continuous part. Yeah. So let me show you the Clara theorem. Yeah. This theorem, fxy and fyx are both continuous functions on disk D. And here we don't have that, right? We don't have these 2 functions are continuous on disk D. Yeah. We only have exists. Yeah. So that means may not be continuous. Yeah. So you miss that condition, then this one may not true. This equality may not be true. Okay? All right. So here I can show you a counter example. Yeah. Yeah. Let me show you. I found a counter example. F of x and y is defined in this way, this formula. For xy not equal to the origin. Yeah. But we define f of 0, 0 equals 0. Yeah. And this example, so you can see after calculation, yeah, the calculation is not easy. So the calculation, you may need to use the powerful calculator, symbolic calculator. Yeah. So the online in this situation, you can use the Wolfram alpha. Wolfram alpha to do symbolic calculation. Okay, yeah. So you can calculate x, a, b, y, a, b, yeah. And you also calculate right, yeah. Yeah. So here in this example, these two functions not continuous at 0, 0. Not continuous. Continuous. At 0, 0. Yeah. And then, so when you calculate AB, yeah, and BA, not equal. Okay? Yeah. Yeah. And here at the origin, when you do calculation, you need to use the limit. Yeah. Yeah. So this calculation is not easy. Yeah. Yeah. Pretty complicated. Yeah. Yeah. So after I figure out, yeah, the whole story, yeah, pretty complicated. After I figure out, I can record a video to show you. Yeah. If you are interested in this counter example, yeah, I can show you that. Yeah. But here for the question, you need to compare with this, the condition of this theorem, yeah, and the condition, part of the condition is missing. Yeah. Continuity requirement missing. Yeah. All right. Yeah. That's the question number 8. Number 9, yeah, local linear, this concept. Yeah. So then the question, the answer is no. Yeah. Because also the condition is missed a little bit. Yeah. Here, look at the condition. F function satisfies condition. Exists, also exists. All right? Yeah. Exists. Yeah. So then, not strong enough. Not strong enough. Yeah. So let me copy the two related statements yeah, we learned before. So let's do comparison. The first one, if fx, f sub x ab and f sub y ab exist and are continuous. See? The continuous, this condition is missing. Yeah. Containing. Then, because with this one, but this statement is differentiable. Yeah. It's different from local linear, but they are closely related. Yeah. Although in this statement, what you see is this differentiable conclusion, different from what we want to have here, the local linear, but next statement you can see. They are closely related. By definition, this function is differentiable if exists and then locally linear, right? Yeah, exists we already have, right? Yeah, exists we already have. So we need another local linear part. Then these three things adding together equivalent to this differentiable condition. So here you can see, yeah. So the conclusion, differentiable, we have it. This differentiable condition contains the local linear property. It contains that. So we have that. Yeah. But still, one important condition is missing. Yeah. So that's number 9. Yeah. All right. The last question, number 10. This time, linearity principle. Yeah. No. Yeah. So this one, 91. Yeah. The highest miss rate. Highest. Yeah. Let me explain why. Yeah. The problem is at the right-hand side, Rx function. This function is not equal to 0. Okay? Yep. So let me, give you the whole picture here. Yeah. All right. Homogeneous. Homogeneous second order linear ODE. Yeah. Then we have the linearity property. That's correct. Yeah. But here, right-hand side, make it non-homogeneous. Okay. Yeah. In class, I did one example, similar example. Yeah, one. Yeah. Showing you why that example. Remember, I remember that is the y double prime plus y equals 1 example. Okay, you can look at that example. Here, you compare this one and that one, quite similar. Yeah, the problem, the same problem. Yeah. All right. So here, first, I just show you if you have two solutions, y1, y2, two solutions. y1 satisfy the equation 2y equals y2 also satisfy this equation. Now we need to consider linear combination. Combination of y1 and y2. So y3 equals c1 y1 plus c2 y2. We want to see if y3 satisfies this equation. Right? Yeah. So y3 double prime plus 2y3 equals c1 y1 plus c2 y2 double prime. Okay? That double prime we can, put it inside. Plus 2 c1 y1 plus c2 y2. Okay? All right. Equals c1 y1 double prime plus 2y1. Right? Plus c2 y2 double prime plus 2 y2. Okay, yeah. Then c1 times x1 squared plus 1, c2 times x squared plus 1 equals c1 plus c2 x squared plus 1. If you compare it with the original, because c1 plus c2 could be arbitrary constant, right? Arbitrary constant. So y3, you can go back here, does not satisfy the original ODE. Yeah. So that means y3 is, in general, it is not a solution of the original ODE. So that means the linear combination of two solutions is not a solution in general. Okay, all right, yeah. But in class, I also introduced a concept called the linear interpolation, right? Yeah. In class, I also introduced a concept called a linear interpolation. Concept. Okay, yeah. So here, if we consider linear interpolation of y1, y2, 1 minus lambda y2. If y3 equals this special linear combination, so it is a linear interpolation. Yeah. Then this time, this y3, if you plug in, it is a solution of the original ODE. Yeah, because after you plug in C1, C2, right? Yeah. So your C1 equals lambda, your C2 equals 1 minus lambda, right? So your C1 plus C2 equals 1. Yeah, 1 times x squared plus 1, that's the same as the right-hand side, our function. Okay? Yeah. It's correct. See? Yeah. So here you can see for the non-homogeneous second-order linear ODE, yeah. So when you combine two solutions, you should use the linear interpolation way, not the linear combination way. So, but the linear interpolation way, we cannot say it has the linearity principle, right? Yeah, not linearity principle. Okay, yeah. So that's the last three questions. Okay, yeah. So try to, so here you can see for these three questions, especially number 8 and number 10, these two questions with very high miss rates, you need to pay attention to some details. Yeah, important details. Yeah. So you need to compare with the, original definition, original description. Yeah, see how different they are. Yeah. Okay. All right. So let me stop right here.